Thank you, Marcell, for being here today. Marcell is with Silka, as far as I know, and
Yes.
in the embedded sector. I think he will introduce himself again. And he has a lot of experience, I guess, in breaking things and hopefully in fixing them as well and teaching us how to do so. So please give him a welcoming applause for today's session.
Yes, so welcome everyone. I hope that I have enough experience to give a good presentation here. This will be the trial run of this presentation, so at the end I also accept some input, some criticism. But the talk, so welcome everyone. This will be a talk about hacking and securing C++. I don't want to take much time with introduction. My name is Juhasz. I am an embedded engineer and I love C++. That's about me, and I work at Silk Engineering as an embedded developer, embedded software developer. We are service provider company, so if you need help with any project, then feel free to contact us. As of my QR codes, all of the work that I've done to prepare this presentation, so all of the source code and everything is available or will be available on my GitHub. So you will be able to check it out there. It's private right now, but I will make it public later. Okay, so what this presentation will be about, I will first tell you a little bit about the setup, how I did the work behind the presentation. Then I will talk a little bit about some important concepts that we need to understand before we can go into understanding these memory-related issues. And then we will go into the bugs that I want to show you. We will reach or touch three main areas, one of them being the stack. So we will first look at the stack. We will see how the stack works, how it relates to C++, and we will see some bugs that are related to the behavior of the stack and also combined with some programming mistakes. We will similarly look at the heap, and after that we will look at buffers and buffer overflow issues. At all of these three areas, first we will look at some primary concepts or behaviors. We will look at how the memory bugs arise. We will look at how they become vulnerabilities. And we will see how they can be exploited by an attacker. And I will also give you some ways or some advice how to mitigate these issues. My hope is that by the end of this presentation, you will know more about these bugs, you will understand how this works, you will meet them, and when you see them in code, or you see the potential for them in code, then you will recognize it, and then we can get to a safer world. And of course, the simplest answer is always don't do it, but we will go a little bit deeper than that. Setup. The setup is simple. I have an embedded device. It's actually this little thing right here. It has a microcontroller on it, and it speaks some binary protocol, serial protocol that I can talk to over the USB of my PC. And this little device consists of a main board, an add-on board, and the case. It's not really important. I just wanted to mention it because all of these, the design files will be available on my GitHub. So if you want to have one on your own, you can download the files and let it be manufactured. I also want to mention that the talk is not specific to embedded devices. I use this little embedded platform because the memory architecture of an embedded device is much simpler. It's stripped down. There is no operating system, so it's much easier to understand these memory-related issues and see how these work. As I mentioned, if you have a software that doesn't communicate with the outside world, then you are safe. But then why did you write the software? We are communicating over this simple message protocol. We need to understand the basics because we will use it to attack the device. It's really simple. We have 1 byte for the message. This can be either a request or a response. There is a subtype. So if you send a request, it can be, for example, a login or a logout request. And as response, you will get a failure or a success response. At the end of the message, there might be some payload. It is optional. If you don't have any payload, then the payload length is set to 0, and you don't have any payload. If the payload length is more than 0, then you have some payload at the end. What it is, that will depend on the message type and the subtype. So for example, if you wanted to authenticate yourself to this device, then you can send a login request. The message type is a request. The subtype is an authentication, and it has the password as the payload. Also, never send passwords over messages. That's really important. And as a reply, you will get either a success or a failure, depending on the password that you send. Let's look at the memory model that I will be using today. And you probably also know this memory model from your C or C++ journeys. We usually get introduced to it early on. We probably never really truly understand it, but we see it sometimes. So on most microcontrollers, we have a continuous memory space. And in this address space, we have different devices mapped to different regions in memory. So for example, we have a flash memory, which is a non-volatile memory, a persistent memory, meaning that it retains data even if the device is powered off. We also have a RAM-type memory, which is a volatile memory. So when you compile your C++ or C or C++ project, then the compiler takes your code and converts it or arranges it into some groups or sections that we call them. And where these sections will land in memory, that is the job of the linker to decide. So here we have a vector table section. On this microcontroller, this contains some important information for the microcontroller, also during runtime, but also during the boot time. The text section, this contains all of the compiled machine instructions. These are the instructions that will be actually executed. These are the compiled versions of your functions, your loops, your computations, and all of your instructions. The read-only data, this contains the constant, non-changing, they're not variables, but data. These are, for example, literals that are contained here. And you have another section here, which is the data section. This contains the initialized global and static variables. Here we have a bit of a conflict that we must resolve because you don't really want to have your variables in a read-only memory, and the flash is a read-only memory because you might want to change your variables. But also the RAM is a volatile memory, so if you turn off the device, then you lose the data there. So what happens here is that there is some code in the text section. This gets executed before the main function is even called. And this takes your data section and copies it from flash to RAM. Then you also have another section in RAM. This is the BSS section. This contains the uninitialized global and static variables. This is set to 0 automatically. And this is also done by a small code before the main function in the text section. Your local variables with automatic storage duration, they live on the stack in the RAM. And your dynamically allocated variables live on the heap. Now, it is very common that the stack starts at a high memory address and grows downwards. There are only a couple of exceptions to that, I think. I don't know of any, but I know that there are. And the heap usually starts from a low memory address and grows upwards. And if these two regions collide, then you run out of memory, and then you have a stack overflow or heap overflow, depending on which one overflowed. So this is the memory model that we will be using today. Another important thing, because this presentation will be full with binary data representations, at least, is NDNS. So NDNS of a system defines how data is lined up in memory or lined out. So if you, for example, have this integer variable with this value in your code, this on most systems an integer is 4 bytes, then on a big NDN system, memory is laid out with the most significant byte at the lowest memory address. This means that as you iterate over memory, you will see the big end of the number first. And on a little NDN system, it is the other way around. So there you have the least significant byte at the lowest memory address. So as you iterate over the data in memory, you will see the little end of the number first. To translate it to C++ terms, if you reinterpret cast the memory region of this variable into a character array and you access the 0th element, on a big endian system you will find the most significant byte, and on the little endian system you will find the least significant byte. And most systems, most modern platforms, also this microcontroller, and most microcontrollers work with little endian representation, so you will see that on the slide as well. But the network byte order is usually big endian, so you will also find that on the slides. This, just to be clear. Okay, that's about the introduction, the basic concept. So let's look at automatic storage. So let's see how the stack works. As we have seen before, the stack commonly starts at a high memory address and grows downwards. This means that you have the stack high in the memory and you have available memory below it. And you have the stack pointer, which is a hardware register that points to the end of your stack. Now, if you have a local variable, for example, this integer variable, then memory or storage will be automatically allocated and deallocated for it, hence the name automatic storage duration. So when you declare this variable, then this means that the stack pointer will be decremented by 4. 4 is the size of the integer, and this newly allocated memory will be used to store the integer. It is very important to note that this integer or this memory is only initialized if you, as the developer, initialize the variable explicitly. If you don't initialize the variable, then the variable will have whatever value there was on the stack before you declare this variable. The deallocation is also automatic. This means when the variable gets out of scope, then the stack pointer is automatically incremented, and this way the allocated memory is reclaimed. And here it is also important to note that the data is not cleared. So whatever data you had in your variable is still on the stack. Or it's not on the stack, but it's below the stack in the free area. So the way we will attack this device during this presentation is that this is our device. There are messages that are received on the device. These messages are received into a buffer. This buffer is deserialized into a message object. The message object is processed. The necessary computations are performed on the device. A response is prepared. This is also a message object. It gets serialized into the buffer and sent back as a reply. It's a very simple workflow. And the message that we will be using here to attack the stack behavior and some programming mistake on this device is the temperature message. We can send a temperature request to the device, and we assume that there are 8 temperature slots on this device. So this device is capable, theoretically, of handling 8 temperature sensors. This means that in the reply, you will have 8 temperature values. You have 8 slots, but not necessarily all of the temperature sensors are connected. Therefore, there is an indicator byte at the end of the message. So if there is a temperature connected to that slot, then there will be a 1 in this indicator byte. Otherwise, there is a 0. This way, you can see which temperature values you should be using and which ones are invalid. And let's see how the exploit would look like. It might not be that obvious at first, but the workflow is that there is a user that goes to the device, they log in, they use this very secret password to log in. This binary data is sent to the device. The device looks at this binary data, looks at the password, and sends back a success because they said a good password. Then they log out, they are done, and they log out was successful, so they leave the device. Then another user comes in, and they send a temperature request to the device. And sending a temperature request doesn't require you to log in. And then they got a reply. And on the user interface, everything looks good because you see that you have only 1 temperature sensor attached to the device. The measured value is 151. So everything looks good, except if you look at the binary, then you will find the very secret password in the response of the temperature request. So what happened here? What's the vulnerability? How does it look like in memory? We have the stack. We have this buffer allocated on the stack. This means that, somewhere on the stack there is this buffer. The first mistake that I did, I didn't initialize this buffer, meaning that whatever value there was on the stack is now in my buffer. There comes our login request. The login request is received into this buffer. It is written into the buffer, but the buffer is on the stack, meaning that the message is written onto the stack. The message is then processed, the response or reply is prepared, and it is also serialized back into the buffer before it's sent out. So it's also written onto the stack, and then the reply is sent out. Everything looks good so far, and then comes the temperature request. As you can see, automatic deallocation doesn't wipe the memory, so your very secret password is still on the stack or in memory. So when you allocate this buffer again on the stack, you will have whatever value or whatever data there was in the memory before you allocated the buffer. So you receive this temperature request. Again, it's written onto the stack. It is processed, and the reply is prepared. Preparing the reply means iterating over the temperature slots, and when you find a slot where the temperature sensor is connected, then you set the corresponding value in the message object. So as I iterate over, I did not bother setting the invalid values because I set it either way in the indicator byte. So as you can see, these values where there are no temperature sensors attached to the device are windows onto the stack, and whatever data there was in the memory before you allocated the buffer is sent out as a reply to this temperature request. So this is how you leak sensitive information. So what have we learned from the stack? We have seen that local variables with automatic storage duration are allocated on the stack. This happens automatically, hence the name. We have also seen that stack allocation doesn't modify the underlying memory, meaning that if you allocate memory on the stack, there is some data which will become the value of your variable if you don't initialize it, and also the allocation doesn't wipe the memory. So again, from that comes that uninitialized stack allocated variables are windows onto the stack. If anyone gets hand of these variables that are on the stack that were not initialized, can see what values there were in the memory before. And that can be dangerous. So what can you do to mitigate these or to avoid this vulnerability altogether? It is very important to always initialize all local variables, even arrays. I would even go so far to initialize every variable, not just the local ones, but the local ones are the most important. And we are C++ developers. We are not C developers anymore. We can use classes, and we should implement proper constructors that initialize all of our variables. Another thing that you can do occasionally is that if you are handling sensitive information, then after you are done handling this information, you can wipe the memory. And again, we are C++ developers. We have classes, we have destructors, so we should implement proper destructors for our classes, at least put some memcopy in it and wipe the memory if we are handling sensitive information. If you are not, then there is no reason to do so. It's just an overhead, but if you're handling sensitive information, then you have this option. So that's about the stack that I wanted to mention you. There are probably other bugs on the stack that we could look at, but I want to touch on the other two areas as well. And the next is dynamic memory allocation. From my experience, there is some black magic feeling regarding dynamic memory allocation. At least I had this feeling when I learned C and C++, because all you learn about this is that you use new or malloc to ask the operating system for some memory, and the operating system is nice enough to provide this memory. And when you are done using it, then you explicitly have to call delete or free to give this memory back to the operating system. But whatever happens in between is the question, and I think it's much simpler to understand how dynamic memory allocation works on an embedded device because you don't have an operating system to hide all of the implementation details. So let's look at how a simple heap allocation works. One of the most important things to point out here is that by the stack and the behavior of the stack, such as the growth direction, is defined by the hardware and the compiler. The behavior of the heap is more of a runtime implementation detail. So it's not declared neither by the compiler nor by the hardware. It is you, the developer, that can flexibly change this algorithm on most platforms. Not on all platforms, but on embedded system platforms, you definitely can do that. So you have the heap, you have available memory above the heap, and then you want to allocate some dynamic memory. So dynamic memory allocation is always handled by the C library. So even if you call new will allocate memory using malloc, and it will construct the object in the allocated memory. And what the C library does, so how malloc is implemented, depends on what C library you use. That's also not constant. So for example, on an embedded system platform where we use the newlib usually, when malloc will need memory, so if you allocate memory, you will ask malloc to give you some from its memory pool. If malloc runs out of memory, it will turn to the SBRK function, which will execute the dynamic memory allocation algorithm. On a Linux platform, for example, where glibc is commonly used, this will happen through the brk and mmap system calls, and this is where the operating system will take over. But focusing on the simple solution, there is this SBRK function, which if you have a microcontroller-based device, then the manufacturer will provide you with some default implementation here. And this default implementation on this device is very simple. All it does that when malloc needs memory, it calls the SBRK function. It increments the heap pointer. So there is this pointer that points to the end of the heap. This pointer is simply allocated, and the allocated memory is returned to malloc's bookkeeping, and then malloc will take this memory over and give you some to use. So this is how malloc gets its memory, but how do you get the memory as a developer? Malloc stores the available memory in a data structure called the free list. You can think of this as a linked list of free blocks. Now, modern malloc implementations are more complicated. They divide up. They have more free lists, or it has more free lists based on the size of the available slots, just to optimize performance. But on a conceptual level, you can think of this as working with a single linked list. And if you ask for memory from malloc, then you also provide a size. Malloc will look through the free list, and it will search for a suitable block for you. And if it doesn't find a suitable block, then it will call the SBRK function and ask for more memory. If it finds a suitable block, then it will remove it from the free list. If it is too large, it will also split it, and this newly allocated memory will be returned to you as the user. And if you free this memory, then this memory gets inserted back into the free list. This is also how memory fragmentation works, but that's then a different topic. The point here is that we must see is that if you have an object on the heap that you allocated and you are done using it, you deallocate it, you call delete. Then this block will be returned to malloc's bookkeeping, and afterwards, if you allocate a new object of the same type, for example, then malloc will look through the free list. It will search for a suitable block in the free list, which it will find, because that will be a perfectly sized block, and it will return that block to you that you have already used and freed. And free doesn't wipe the memory again. So that will be used again in the next allocation. So there are two bugs here that we could look at. This one we will skip because this is the reuse of memory. We have also already seen at the stack, this is very similar, that as I've said before, you allocated an object, you freed it, you asked again, and you will get the same memory. But malloc does not touch the underlying memory. It means that it will not automatically initialize that memory for you, and it also, or free, will not delete that memory or wipe that memory. So again, if you don't initialize your dynamically allocated variable, then whatever value there was in the memory before will be the value of your variable. And that way you can leak sensitive information again. The other bug that I want to look at is the use after free bug. This is also referred to as dangling pointers, and we will see what they are and how they are dangerous. Now, the exploit for this that I came up with is that this device allows a one-time login process. For example, if you forget your password, you go to the device and you start this login process. The device will generate a password on its end. Maybe it will send it to you on your phone. Of course, this device doesn't do that. It's just a conceptual game. And if you enter the correct password, then you can successfully log in. Now, if you enter the wrong password, then access will be denied and you cannot log in. But what happens if you start the one-time login process, then you manually cancel it because you don't need it anymore, and then you go there and enter any password that you want. You will find that you can log in with any password, even wrong password or whatever you wish to enter. So what is the thing that happens in memory that can achieve this behavior? So this is the code that is intentionally written bad so that it contains this bug. And there are two places which are the most problematic. One of them is this, because here this one-time password is the one that is generated on the device when you start the process. If you cancel the process, then this one-time password will be deleted. You give the memory back. At least you don't have a memory leak. But you don't set it to, or I didn't set it to null pointer, which means that I now have a dangling pointer in my code. And this line here, this is where I compare the user-entered password with the generated one, and here I am potentially using a dangling pointer. But why is this a problem? In memory, this looks like the following. I get a message on the device that starts this login process. This will generate this one-time password. For the one-time password, it will allocate some memory on the heap. This means it will call new will call malloc will return this memory from its bookkeeping, or maybe it will call sbrk. The point is that malloc returned this memory. Then a success is sent out. Then you cancel this process. I receive this one-time password cancel message. This means I delete now this pointer, which means the memory is returned, but the pointer is still, it is a dangling pointer. It still points to a valid memory because the heap is still an existing memory region. You can still access it. And again, a success reply is sent out. And here comes the login. After the cancel, whatever password the user entered, I will allocate a new memory for it. And this is the same size as the password because both are password objects. And malloc will find a suitable block for it in the free list. It is the block that I have just freed, which is the same one. And here I have two pointers that are pointing to the same memory location. And when I compare them, this will always give me a true or a success. And success reply will be sent out. So this is the danger of dangling pointers, or one of the dangers of dangling pointers. So what have we learned here? From the heap, we have seen that variables with dynamic storage duration are allocated on the heap. We have also seen that malloc does not initialize the memory for you automatically, and free does not wipe the memory. This means that if you have an uninitialized variable allocated on the heap, you potentially have, or you definitely have, whatever data there was in memory before the allocation, but you might have some sensitive information in that memory region. We have also seen that dangling pointers are dangerous, that we have demonstrated. So what can you do? Again, you must always initialize dynamically allocated variables. We are, again, C++ developers, so you wrap your dynamically allocated objects into some classes for automatic lifetime management, but also you use some constructors to initialize the memory properly. And if you're handling sensitive information, then you can also implement destructors to wipe that memory before you return it to malloc. And now you are probably thinking that, yeah, sensitive information, I'm not handling passwords, so what's the worry? But we will see later at the buffer overflow bugs that not only passwords are sensitive information. If you leak addresses from memory, that can be just as devastating, if not more dangerous. And last suggestion is to avoid dangling pointers. Of course, that's easier said than done, but a really good way to do it is to avoid using row pointers. So again, C++ developers, we have really good smart pointer implementations. We should start using them, at least for ownership. If you are just giving out memory to handle, then you can still use row pointers, but use smart pointers. That's it about the heap, and let's go to a more complex and more interesting topic, more fun. It's buffers and buffer overflow. So what is a buffer? A buffer, or an array, is a continuous array of elements of the same object. So for example, here we have different variables, and we also have this integer array, which is laid out in the stack. Now, as we discussed before, the stack grows downwards. This means that when you allocate variables later, they will have a lower memory address, but arrays grow in the other direction. They grow upwards. This means that the 0th index will have the lowest memory address, and the back of the array will have the highest memory address. And this is also the intuitive way to use pointer arithmetic. So if you're iterating over an array, you expect that if you increment the pointer, then you will get the next element in the array. And if you think about it, the pointer is just a memory address. So this is how the arrays are laid out in memory. So what is a buffer overflow? As the term states, it is when your buffer overflows. This means that you over-index it. If you have plain arrays or C-style arrays, then you have no boundary checking. This array, this R variable, is simply a pointer to the beginning of the array, and it is your job as the developer to keep the size of the array in check. This means that by doing some mistake, for example, by using this memcopy simply takes 2 pointers. It doesn't care about arrays or objects or whatever. It takes 2 pointers and the size, and it will happily copy from one array to the other without any boundary checking. And this, if we do this, then we will go into undefined behavior territory, which we will see can be dangerous. Before we can look at the actual bug, one important thing that we must also understand is function calls. So how a function call looks like under the hood, or when it is compiled, because this is the thing that gets exploited the most. So at the beginning of the function, so of course this is the assembly representation of a function call. So if you write a function in C++, then compile it, then you will get this. At the beginning of the function, there are some registers that are pushed onto the stack. So this means that these registers are backed up, the values. These are the registers that are used in this function, and their values are backed up so that when the function returns, they can be popped back into the registers, and the function, the caller function that called this function, can continue execution without any issues. The most important register here is the link register, that's the LR at the end, because that contains the return value of the function. So you have the return value in the link register, which is then pushed onto the stack. Here, the stack pointer is decremented by some value. Here it is 300. The size is whatever size you need for your local variables. So this is how automatic storage duration works. The space for your local variables is allocated automatically. This part is not that important for function calls. It's just interesting to see that this, for example, here is how your C++ variables are handled on the assembly level. So you have this x integer variable that gets translated to some offset in relation to the stack pointer. And this is how it is referenced. At the end of the function, the return value is prepared, and then the stack pointer is restored, meaning that whatever value you or the compiler subtracted it from it at the beginning is now added to it. And at the end of the function, the registers are popped back in. This is important for the caller function to execute or to continue execution without any issues. But the most important thing here and the most interesting that we will have fun with is the link register, because look at how the link register is handled. So you have the return address of the function. It is stored in the link register. It is pushed onto the stack because the link register can be reused again. And at the end of the function, it is popped back in, but not into the link register, but into the program counter, which means that the execution jumps to that address, meaning that this is how you return. So what's the vulnerability here? How does this all come together with a buffer overflow bug? So here we have the stack. We have some buffer on the stack with a buffer overflow bug. This buffer grows upwards. If you have a little overflow, then you can still reach some local variables. You can modify the values of these variables, and this can be devastating if you are handling or if you're calculating prices or whatever the function does, if you're controlling motors. If someone can change those variables, that is not good. But if we go further, we can also affect the behavior of the caller function, because these registers that are pushed onto the stack are backed up for the caller function to continue execution. So by changing these values, you can mess around with the behavior of the caller function. And the most fun thing that you can overwrite is the return address, because this will allow you to basically hijack control flow of the program. You can do anything. And this is what hacking actually means. This means that there is a device or a software that you are using in a way that it was not meant to be used. It was not designed for that purpose, but you are still using it that way. So let's see what we can do. This is how the bug looks like. It's not that straightforward to see in a large code base or to detect. The point is that we have some array laying around in our code. It is allocated on the stack with automatic storage duration, and maybe you used some size to allocate it. This is the maximum size of passwords, for example, and then later you copy some value into this buffer. So here, for example, if we get a request, a login request from the user, then we take the password from the login request and we put it into this entered password array. And the problem here is that if the payload length is larger than the password size, then you have a buffer overflow. And no one checked the length before. Does this mean that someone forgot to check it? Not necessarily. It sometimes happens that there is a developer, they look at the client side of your application and they see that, okay, this client side application checks the size of the password and it only allows this certain size of password to be sent to the backend, so I'm good, I don't have to check it, it's just a waste of time. But what they didn't consider is that the client side is not, or the client application is not the only one who can send you messages. A hacker will have no problem generating some message and then sending it to random IP addresses. Okay, so let's see how we can exploit this. We will use the login process to exploit it. So what we have here is we have the correct password allocated on the stack, and we also have the enter password that the user will enter. It is also allocated on the stack, so you can see there how it's laid out. Now, if you get a login request with the correct password, then it will be written into the buffer, and access will be granted. The compare function will return a success. If you enter a wrong password and this is sent to the device, then the device will look at it, recognize the wrong password, and access will be denied. Everything good so far. What happens if you send this message to the device? This is a sequence of A characters long enough to overflow this buffer and long enough to override the buffer above it. So now you have an array of A characters in both buffers, which means access will be granted and you can access the device. This is one exploit that we can do, which does not affect the return address just yet. It affects local variables, and you don't have to think in terms of passwords. You don't have to manage passwords. This points out that if there is some other variable on the stack, anything, prices, whatever, a hacker can come in and override those local variables. Another exploit that we can use to attack such a bug is the arbitrary code execution. Here we have our stack, we have our buffer on the stack with the overflow bug, and as seen before, it grows upwards. And the most important thing that we can corrupt here is the return address. So we can write whatever value we want into the return address, as you have seen before with the password. And what we want to do is, if we inject any code before the return address into this payload, and then we set the return address so that when it is popped back into the program counter, it jumps execution to the beginning of our code that we have just injected, then we can basically do whatever we want. So if I wanted to, on this device, turn on an LED, I have to do the following. I need the address of the output data register. I have it in some, I store it in some register. I need the value that I want to write into this register to turn on the LED. I put it in another register. And all I have to do is that take the value and write it into the output data register. This is the register that is pointed to by the address in the other register. This is how pointer arithmetic works on an assembly level. And at this point, the LED turns on. If you have free space that you don't want to use because you have such a huge overflow, or you just want to guess the address where you want to jump, you can insert a bunch of nope operations because execution simply jumps or slides over them. They do nothing. I can also insert an infinite loop here so that the application doesn't even crash. It will just be in an infinite loop. And all I need at the end is the correct return address that points to the beginning of my arbitrary code. And if I compile this, I put it in a payload instead of the password, and I send it as a login request, then I can turn on an LED on this device by injecting arbitrary code. And this is simple, but here you can do anything, whatever you want. So what can you do to avoid this exploit specifically is to make the stack non-executable. So for most applications, it doesn't make sense to have the stack as executable, but, or at least I don't think so, but per default, when you start working, for example, on a microcontroller, so this is specific to embedded devices, you will probably have in the default linker script the stack as executable. So you can just set that to not executable. Okay, so now we cannot inject arbitrary code because the stack is not executable. So what can we do? We still have our buffer overflow bug, we still have our registers, and normally, if it was a normal execution, then the link register containing the return address would point to some code in flash memory, and this is what would continue executing. But I, as an attacker, don't want that code to execute. I want this code to execute. So all I have to do is to fill this space with junk or dummy data and set the return address in a way that it points to some code that I want to execute. So besides, of course, not doing buffer overflows in your code, what can you do to avoid this type of attack? What you definitely should do is limit the code that you put into production. So if you have a code that you have developed, you probably have a lot of debug commands in it. You probably don't need them in production, so you can safely remove it. And then debug commands usually come with more extended area that they can do, so you just remove them. So now we are in a position as attackers that we have a buffer overflow bug, but the stack is not executable, so I cannot inject any arbitrary code that I want. And also, the code for example, turning on this LED on the device simply does not exist in the binary. So can I do anything? Of course I can. This is where return-oriented programming comes in. This is the idea behind return-oriented programming is that you are looking at the binary and you are jumping around in the binary, executing bits and pieces of different functions, doing multiple returns until all of your desired registers are set to the desired values and you executed all of the instructions that you wanted. So we have our buffer, and my goal is to turn on the LED. I have to carefully think about what I want to do. I want to have the value 2 in some register. This is the bit mask that I need to turn on this specific LED. In another register, I need to have the value of the output data register, because that is the one that controls the state of the output pins. And then I just do a simple pointer arithmetic and store the value in the register. So I look around the binary and I find the so-called ROP gadgets. This is the first thing that I find in the binary. This is not exactly the code that I want, but it is a good start because here I have the value 2 that is stored in some register. It's good enough for me. It doesn't matter which register it is stored in. And it also restores the stack pointer from the R7 register, because it's also really good for me because I have control over the value of R7 register through this overflow bug. So what I do, I set the R7 register in the overflow bug so that it points to some other location that I want to. And this allows me, because at the end of this gadget, the program counter is popped back, meaning that I can jump again. The return address is popped back again from the stack, and I just set the stack here, so I can do another jump. So I look further in the binary, and I find this other gadget that I was looking for. This gadget also does something for me because it stores whatever value is in R3 register in the R7 register incremented by 4. This is also really good because I have control over what goes into the R7 register. So if I play my cards correctly, I tick all of the boxes of the requirements, and at this point, this LED turns on. So if I put all of this into the correct order in the payload, I send it instead of the password, I will get this LED turned on, and I will do it I can do it in a way that the stack is not executable, so I cannot inject arbitrary code, and the code for turning on this LED doesn't even exist in the binary. I just jump around in the code remotely, and I can do whatever I want again. And then you might be thinking, yeah, that's not that interesting because you just turned on an LED. That's not that big of a deal. But this return-oriented programming thing that works really great on modern platforms as well. So if you think about a shell, when you open a shell on Linux, for example, what you do or what is executed behind the scene is that this exeq system call is executed as a system call. And what that means on an x86 platform is that on the RAIX register, you have the value of the execve system call, which is 59. In the RDI register, you have the address of the bin.sh string, which you will have in your binary, because whenever you are making a system call, this bin.sh will be there. So if you have a complex enough application, it will be there. And the RSI and RDX registers are set to 0. If you execute a system call with the registers having these values, then you will get a shell. So what does that look like? You have the stack, you have the buffer with the buffer overflow bug, and you have your binary. I look around in your binary, and I am looking for these ROP gadgets again. And this is the code that would normally execute, but I don't want this code to execute. I can, because of the overflow bug, I can set this return address to whatever value I desire, and I can jump to my first gadget. What my first gadget does is that it pops the RDI register and then returns. The RDI register must contain the address of the bin.sh string, and the string is there in your binary, so I just insert its address into the payload. And then again, this gadget then returns, meaning it pops the return address, and I can jump again to the next gadget. The next gadget pops the value of RSI. The RSI, or the value of RSI, is 0. Now I have that. Again, I can jump to the next gadget. The RDX register, again, value is 0. Simple, I just put it in the payload, and I put the address above it for my next gadget. This next gadget pops the value of RAIX. The RAIX register must contain the system call number of execve, so that's 59. That's also pretty easy. And then I put the address of my final gadget. This final gadget makes a system call and returns, but it doesn't return because at this point I have a shell, an interactive shell. So this is how you can use return-oriented programming to open up a shell, and you just jump around in the code, execute bits and pieces of other functions called or referred to as ROP gadgets. So what can you do to avoid this vulnerability altogether? As you have seen, this jumping around in the binary, this all relies on my knowledge about fixed memory addresses. On embedded systems, we are mostly working with fixed memory addresses. We don't have an operating system, we don't have virtual memory, but on a modern platform, you have an operating system and you have virtual memory. And another thing that you have is address space layout randomization. So if you compile code on a Linux platform, you won't get fixed addresses in the binary, you will get offsets, you will get a position-independent executable, which means that when the operating system starts that process, it will get a randomized address space assigned to it. And if the attackers have no knowledge about the address space that you are in, then this nullifies the ROP attack. That is, unless you log something. If you do a debug log about that includes some memory addresses of variables, of functions, whatever. For example, if your program crashes and you print out the stack because it's good for debugging, then an attacker can look at it, and the protection offered by address space layout randomization is nullified. So this is why, for example, a lot of attackers will start out by attacking your software and trying to crash it, because when a software crashes, then you potentially have some useful debug logs. Okay, so what have we seen? What have we learned? We have seen that buffers grow in the direction of increasing memory, so the stack grows downwards, but buffers grow upwards. We have also seen that buffers are by default node bounded, and they can overflow. It is the responsibility of the developer to keep the size of the buffer in hand. That is, unless you use C++. We have seen that buffer overflow can corrupt the stack, and buffer overflow basically allows attackers to hijack control flow. So attackers can do basically anything with your code and with your device. We have a lot of protection mechanisms that we can use. So for example, we only include code in our program that we actually want to execute. We use C++, that's really important. We have the ability to tie or to bind the number of elements or the size of the array to the array itself. We use encapsulation. And there are a lot of really nice containers offered by the standard library. We have vectors, we have arrays. If we use it properly, we can use range-based for loops. And with the range-based for loops, for example, you cannot overflow an array that is properly implemented, of course. You never rely on client-side verification. The client application is not the only one that can send messages to the backend. That is really important. You avoid raw and historically unsafe C functions, like memcopy, for example. Of course, you still need to use them if you want to set a memory, but the point is that if you use it encapsulated in a class where you have the size in hand and the data structure, then it is basically impossible to use it incorrectly. And on the outside, you use copy constructors, you use copy assignment operators, and you use C++. It is also very important to help ASLR. This is the address-space randomization. This means that you don't leak information about the memory, no addresses of local variables or any variable or function addresses. That's even worse. Because then, if an attacker sees it, then the protection is nullified. If you are a system developer, then you have even more options. On one hand, that's not so easy, but you could use ASLR, but there are some other protection mechanisms, such as the non-executable stack, stack canaries, and other protection mechanisms that you can use on a system level, but that's not in the hand of the C++ developer. And the conclusion is I just want to briefly iterate over it. It's nothing new. It's the things that I have already listed. These are the protection advices that we have seen. But the most important conclusion that I want to draw your attention to is to use C++, because C++ is a really good way to avoid most of these bugs. In C++, we have a lot of really nice features. We have arrays where the number of elements are tied to the buffer. You cannot overflow them. You have shared pointers or smart pointers for getting rid of dangling pointers. You have references, encapsulation. You can write constructors, destructors. You can do a lot of things. And if we leave behind these C programming, so if we don't continue being C programmers wrapped in a C++ wrapper, but we start really using C++, then most of these bugs will naturally disappear, and that would be a really great thing. Thank you very much for your attention. I hope you enjoyed it.
So I think we have a little time for questions. René, what's your opinion on time?
Yeah, I think we can answer the one or the other question. So
we have a microphone.
We've got two.
We got two. Yeah.
Thank you for the presentation. I have one question. Looking retrospectively, having a stack that grows backwards seems more unsafe. Wouldn't be, I mean, I know that you cannot control that because it's the CPU, but wouldn't be much more safer if it's going the other way around?
Yes, I think it would be. And I also searched a lot for why it grows downward. And apart from some historical reasons, there is only one good reason that I see why it grows upwards or downwards. And it is, if we think back, can I go back? Interesting. When we looked at the stack, at the function call, sorry, just a sec. Yeah, this is the function call. So if you see this, then this is how your C++ variables are referenced on the assembly level. And this is the only reasonable answer that I found why the stack grows downwards, because if it would grow upwards, then here you would have a negative index. And that's not that intuitive. I don't think that it is a hardware capability. I know that historically there was some hardware that could only add offset to the stack pointer, so it might be the reason for it. And also, I know that there are some exceptions to this rule, but yeah, generally speaking, I also don't know why it's this way, and not many people know from what I found on the internet.
So which of possible mitigations are actually available on microcontrollers? We talked about making the stack non-executable and ASLR, and then there is data execution prevention, but doesn't the OS do all of those things?
Sorry, doesn't?
Doesn't the operating system do all of those things?
Yes, most of those things. I would say that from this point on, it's the job of the operating system. So the non-executability on the stack, I think on a Linux that's default. So you have to explicitly set it to executable. So you have control over that, but that's also the job of the operating system. On an embedded system, you have to set it in the linker script. Just remove the X from the access rights. And yeah, ASLR, I don't know if that's even possible on a microcontroller. Probably you could. But yeah, I have never done that. I think the stack canaries that can also be a compiler option, but I'm not sure there.
Hi, thank you for the speech. And do you know of any C or C++ compiler which does the stack the other way around?
No.
No.
And I'm not sure that it's only the compiler.
Because I think if the compiler would do it, we would be more safe, but you could not call any other library function.
Mm-hmm. Yeah, I'm not sure if that's... I think that depends on the architecture. Maybe I will not be able to find it, but on the... so on the assembly level, I'm not even sure that this assembly instruction is available with a negative integer. I'm not sure there if it would be possible solely on a compiler level, but that would be interesting to look into. Thanks.
Hi, thank you for your presentation. It was really interesting. I actually have two questions. So first is about the tools that you can recommend for the automatization of the vulnerability analysis. And the second is, do you see some cases when it makes more sense to analyze the assembler code more than the C++ code?
Yeah, so on the first question, I'm not sure I can recommend anything. I mean, I have used static code analyzers before, but not consistently. So whatever the client prefers, we usually use that one. It's not that they usually puke out a lot of errors, a lot more than would be necessary. And I don't think that I have a favorite there. On the other note, I don't think that it makes sense to analyze the assembly level. Unless you are specifically designing for a really specific hardware, then it doesn't make sense, because on a C++ level, the C++ doesn't say anything about the assembly that comes out in the end. So that will depend on the hardware and the platform and a lot of things.
Maybe I can add something to that question, because turning up the compiler warnings and also static code analysis will, for example, tell you about uninitialized data. So you can get rid of those problems based on the compiler. C++26 will also automatically not let you reuse memory that easily. So, for example, if the password was on a stack and the frame is reallocated later on, it will not show the password anymore. That's basically fixed with C++26. Yeah, and the language is also developing in this regard. There's the standard library hardening, also in C++26, which you can enable to trap when you overrun a buffer, for example, of a STD vector or something like that.
Yeah, that's a really good input. You should always compile with all of your warnings enabled and all of the errors. But that's hard to do if you are compiling legacy C code, because then you will have a lot of errors.
So, second part of the question.
Second part?
There was a second.
That was about. What was it about? Sorry? Analyzing the assembly code. Yeah, that was if it is worth it to analyze assembly. Yeah.
Hello? Yeah. Okay, thank you for the great presentation. The question is, for preventing to reuse deallocated memory or accessing deallocated memory, is it useful to just call memset 0 on an address before deallocating it?
Yeah, so if you're handling sensitive information, then sure. I'm not sure about this, but I think the best is to set it to FFF, because for some reason the ones overwrite it better, the memory. If you set it to 0, then I think that even if someone gets hand of the device, they can still read the data. But that's only if you're handling really sensitive information. Otherwise, I wouldn't just wipe the memory after every class, because it's just the huge overhead.
Also thank you for the talk. It was really interesting. Just a quick question. Have you noticed any difference in performance or in memory usage when you use C versus C++, especially with STD vector and everything?
No. I've done a presentation about that last year. That's more specifically about embedded system and how you can balance efficiency and flexibility, how you can add layers of abstractions. But basically, all of the encapsulation, even inheritance on a basic level, so not dynamic polymorphism, but inheritance, those are all zero-cost abstractions. So vector doesn't add any overhead. Of course, the boundary checking will add overhead, because you will have an extra if. If you write your own classes, the initialization of memory will add an overhead, but not the constructor itself. So it's the overhead of the extra functionality, not of the encapsulation itself.
Okay, thank you very much. We're running out of time. Just about this performance thing, Louis Dion gave a talk about library hardening, and he mentioned some numbers about this overhead. If you add it from the library perspective, like the overhead of the boundary check, and they said it was a maximum of 2% in their whole operating system. Costs something, but it also helps a lot. And with that being said, I have to close the session for today. Please give Marcell a final applause.
Thank you.
You're doing great, thank you. And those of you who like to join us for the pizzeria,